Hello, everyone. How are you guys doing today? Good. Okay, so as we decided, our next exam will be most likely after 3 weeks on 24, and our what is called what break? Thanksgiving break. Our Thanksgiving break probably on 26 or 27, something like that. So we are going to have our next exam on 24. 24 is a Monday. And on what chapters or what sections, we're not sure. So I'm going to make a basic review sheet homework based on, let's see how much you can finish this week. And then probably we'll have at least some idea how much you can finish in next 2 weeks. Any question? So we have a homework due on chapter 2, section 2.1, 2.2, not tonight, but Wednesday midnight this time. But if you want to submit it by tonight, feel free to do so, no problem. And also I posted the solution for 1.5. So if you need to see any of the solution, any of the answer, how to do it, you can just check. And also one more thing, the purpose behind assigning you the homework is for you to have practice on the questions or on the topic we go over in class. So if you just give me the answer without doing any work, why do you expect to get any point for that? You should show all the work and then box your final answer. I don't want to see the answer because the answer can be, you can copy answer from anywhere, from ChatGPT, from Google, from Polynomial. Like, answer is not important to submit. I mean, it is important, but answer is not the only important thing when you do the homework. You have to know how to do all the steps so that during the exam, you will not feel so lost and have no idea what's going on in class. Okay? And if you are planning to just submit the answer, expect to see 0 on your homework grade. Okay? I'm warning you guys. Okay, any question, comments, concern, complaint, anything? Nothing? So in our last class, we talked about subspace, and we learned that in order to be a subspace, there are 3 conditions that need to be fulfilled. Number 1 is that our space, it cannot be empty. So we say, well, at least if we have a 0 element, 0 vector in our space, then it's not empty. And then you have to have, it has to be closed under scalar multiplication and vector addition. So as long as these 3 conditions fulfilled, then we can say, well, whatever we have, the set is a subspace for the vector space. And subspace is set of all the vectors that has the same characteristic as the original vector space. That's a subspace. Now here we have 2 questions. It says determine whether these 2 sets, they are a subspace for R3. R3 means XYZ plane. So the first one says we have 3 elements, XYZ or X1, X2, X3, and this set has 1 condition. The third element should be the sum of the first 2 elements. What are the first 2 elements? It doesn't matter. They could be anything. X1, X2 could be anything, but the requirement is that the third element in your space, the third element in your set, it has to be the sum of the other 2. And they're saying, well, if you have a set with this condition, is it a subspace for R3? It means, is it in the R3? Means in your XYZ plane. So to find this out, you have to check all of these one by one. And if you think, or if you already know this is not a subspace, all you have to do is give a counterexample. Then you don't have to show any of the steps. I mean, you don't have to prove any of these 3 things. If you have a counterexample, that's the answer. But if you don't find a counterexample, that means it might be true. If it's true, then you have to show all three things. So we assume this is true, unless you know a counterexample. Can you find a counterexample saying that it's not true for C? Can you think of a counterexample? If you cannot, then you have to prove it's true. So to prove, you have to go one by one. First, we start with condition 1. Oh, what is this? Oh. Oops. My draw is mode.
I saved a seat for you.
Thank you.
You're gonna bump into a chair, so no.
Hold on. So we have a set in XYZ. Our first two elements could be anything, X1 and X2, but the condition is set on X3. It says X3 is the sum of the first two elements. So we check the first one. What's wrong with this? Okay. Let me close it and then reopen it. It's not in the pen mode, it's in ink mode. No. I think it's fine now. The condition 1, we have to have at least 0 element in our set. So we say if you have a 0 vector, the first vector is 0, and then if you add the two elements, 0 plus 0, what do we have? We have 0, 0, 0, which is a 0 vector. So we have 0 vector is inside our S. So these two, when we add, we get the third one. So 0 vector means you substitute your elements with 0 and see what result you get. If you have the same requirement fulfilled with 0 vector, that means that 0 vector is inside the set. So here the first two element could be anything. So we said first two elements are 0. And the third element is the sum of the first two, which is also 0. So we have 0, 0, 0, which is a 0 vector. That means the 0 vector satisfies the condition of the third element. So it's inside this set. Now the second condition says take any two vector from this set, add them, and see if the sum is inside that set. It means when you add the two vectors, the sum, does it fulfill the same requirement? The requirement is that the third element is the sum of the first two elements. So let's say condition 2. Let's say we are taking a vector U from S and a vector V from S. Since we are taking them from S, that means U satisfy condition that U1 and U2, the third element is U1 plus U2. Because it's inside the set, so whatever requirement, whatever condition the set has, we have the same condition inside this vector U. For V, let me do it on the side. If you take a vector V from S, that means our V is, the first one is V1, then V2, and the third element is V1 plus V2. It has the same characteristic as our set. And now we are going to add these two vectors, u and v. So if you add u and v, when we add vectors, we add them column-wise, right? Or element-wise, sorry. So we get u1 plus v1. This is v, not u. u1 plus v1, the first element. u2 plus v2, the second element. And the third element is this plus that. So u1 plus u2 plus v1 plus v2. This is what we have. We added the first u1 and v1 because they're on the first row, first column. Then we added the second element. And then lastly, we added the third element. Now, what do you observe? Whatever we have here, is it the sum of the first two elements or sum of the first two row? Is it? So if we add them, we have e1 plus v1 plus u2 plus v2, which is same as this one, e1 plus v1 plus u2 plus v2. So they are same. That means the second condition also fulfilled. The sum of any two vectors from this set fulfill the same requirement as the set. So it's inside this set. So u plus v is inside the set. And now the last condition, if you multiply one vector with a scalar, the product also has to be inside the set. Means the product has to have the same characteristic as the set. So let me get a page. We take 1, 2, 3. The third condition is any constant, let's say C. Any constant C times U. So C times our vector E1, U2, and then E1 plus U2. So we multiply C E1, C U2, C E1 plus C E2. So you multiply each one of them by your constant. And then you observe. If you add, sorry, not this one. If you add these two, do you get the third element or the third row? We do, right? CE1 plus CU2 the same as the third one. That means our third condition is also fulfilled. So CU vector is inside our set. So all three conditions fulfilled. That means yes, S is a subspace of R3. Maisha.
Why R3?
Because we have three elements, X1, X2, and X3. R1 is a point.
The vector without the subspaces we did, oh, that was L1, L2, and L infinity?
Yes. So if your vector has two elements, it's R2. If your vector has three elements, it's R3. But if your vector is not a vector, it's a matrix, so it's a metric space.
Oh.
So what do you think about A? The condition in the set of A, it says we still have three elements, X1, X2, X3. X2 could be anything, we don't care. But when you add X1 and X3, the sum always has to be 1. So it's set of all the vectors that has X1, X2, and X3. And if you add X1 and X3, their sum is 1. Is it a subspace of R3? Means if you have this set, does it fulfill all three conditions?
Fails all three conditions?
If it fails only one condition, then you are fine. It doesn't have to fail all three. It means you're looking for a counterexample. Can you think of a counterexample? Zero matrix. Good. The zero matrix. It should be 0, 0, 0. So look what happens. 0, 0. So when you add first one and third one, the sum is 0, not 1. So the 0 vector is not inside the set. So it fails the first condition. So we don't have to look for the other two. If it fails one condition, it's not a subspace. And in the exam, I'm going to ask one of these. I'm going to give one set and ask you, is it a subspace for R2, R3, or next we're going to do matrix, and then we're going to do polynomial. So we have 4 space, R2, R3, matrix space, and then polynomial space. There are many other space, but here we're going to discuss only these 4. So we did R2, R3. Any question on R2 or R3? Any question? Comments? Anything? Okay. So this one failed because of the 0. The next one, we are in a metric space. It's asking, determine whether the following matrices are subspaces of 2 by 2 matrix. Okay. So what do we have to do? We have to check if 0 matrix is inside that 2 by 2 matrix space. We have to see some of the 2 matrix we have from the set. Is it still inside this set? And you have to see if you take one matrix from this space and then multiply by a constant, is it still inside the set? So the same 3 operations, but here it's in matrix form. And here I have 1, 2, 3, 4 examples. The first example is set of all 2 by 2 diagonal matrices. So what does that mean? It means if you take set of all 2 by 2 diagonal matrix, do you still get a diagonal matrix after fulfilling all 3 conditions? The next one is a 2 by 2 triangular matrices. You take any 2 triangular matrices and then see after fulfilling all 3 of them, is it still in a triangular matrix form? The next one says all 2 by 2 matrices such that the element in the position 1, 2, it means first row, second column is 1. And if you apply all 3 of them, do you have a matrix that still has the same thing? On the position 1, 2, you have 1. And then the last one says set of all symmetric matrices. Is it a symmetric matrix after you apply all 3 things? So think about them. What do you think? Let's start with the first one, Maisha. The diagonal entries, since it's a 2 by 2, so I mean diagonal entries may be 0, but all of them cannot be 0. That's the thing. All of them cannot be 0, and every non-diagonal entry must be 0.
I think the first one is true.
Why?
Because when you're adding the vectors, the numbers in the new matrix can change. So it might not be 0.
So it says you are taking set of all the diagonal matrices. So diagonal matrix has a format A, B, C, A. No, sorry. A0, A0, 0D. This is what diagonal matrix is. So if it's true, that means you have to prove all three conditions. The first condition is 0. Condition 1. So if you take 0 matrix, 0, 2 by 2, it means 0, 0, 0, 0. Is 0, 0, 0, 0 a diagonal matrix?
No.
Actually, it is. Because in the diagonal position, the other two entries are 0. So the diagonal may be 0, may not be 0.
Okay.
So 0 is a diagonal matrix.
Okay.
That means the 0 matrix belongs to R 2 by 2. Or sorry, I should say S. S is the set of all the diagonal matrices. And then second condition, if we add any two diagonal matrix, do you get a diagonal matrix?
Yes.
Alexander, question?
If 1, 2, and 2, 1 are the non-zero values, is it still diagonal?
1, 2,
Like A1, 2, and A2, 1.
A1, A1, 2. This position.
Yeah, if those are the non-zeros, then it's those are the-
Then it's not a diagonal.
so it has to be.
Everything has to be, I mean, the B and C position, they have to be 0. Then whatever you have here, that's a diagonal. So 0 is a diagonal matrix. And how about the sum of two diagonal matrix? A0, 0, A0, 0, D. And if you add B0, 0, C, these two are diagonal matrix, right? Because we have diagonal, diagonal, and the other two elements are 0. If you add them, what do you have? Go ahead, Maisha.
No.
A plus B, because we have A in the first position, B on the first position. So A plus B, and then 0 on the row wise and column wise. And then the last element, we have D and C. C plus D. And 0. So you see, two are diagonal matrix. So sum of any two diagonal matrix is a diagonal matrix. And the last one is easy to see, right? If you multiply any constant by a diagonal matrix, what do you get? Still a diagonal matrix. So all three conditions satisfied. So yes, the diagonal, a 2 by 2 diagonal matrix, the set of all 2 by 2 diagonal matrix is a subspace for all 2 by 2 matrix. The next one is interesting. We have set of all triangular matrices. Is the set of all triangular matrix is a triangular matrix when you add them or when you multiply them with a constant, or when you take the zero triangular matrix. Maisha,
No.
why not?
Because you can have an upper triangular and a lower triangular.
Good job. That's the trick. Just because you see triangular doesn't mean you're working with one type of triangular. If you take a lower triangular and an upper triangular and add them, do you get a triangular matrix? No. So just because you have a triangular matrix, it's not a subspace for a 2 by 2 triangular matrix.
But if you specify upper or lower, it is.
Exactly. If you specify some set of all 2 by 2 upper triangular matrix, then yes. Or lower triangular matrix, then yes. But when they say only triangular matrix, it fails. The sum is not a triangular matrix. So no. If it's no, then you have to give a counter example. So our counter example is upper triangular plus lower triangular is not a triangular. The third one, set of all 2 by 2 matrices such that the position A1, 2 is 1. That means the first row, second column is 1. Why not, Brendan?
No, it is.
Are you sure? Maisha. Set of all 2 by 2 matrices such that the position 1, 2 is 1. So it's always 1. Why not? Can you give a counter example? The 0, 0, 0, 0 is a 0 matrix. Look at the position. It's not 1. So it fails the first condition. 0 is not inside this set. The set says the second 1, 2 position is always 1, which is wrong. So if it's something wrong, then you just have to give a counter example. You don't have to prove anything. But if it's something true, then you must prove all 3. You must prove all 3 conditions. The last one, symmetric matrix. Do you know what is a symmetric matrix?
It's like mirrored.
It's mirror. So transpose is equal to the original matrix. A transpose and A, they are same. So what do you think? If you have a symmetric matrix or a set of symmetric matrix, do you get a symmetric matrix? Maisha,
No,
why not?
because you can have a 3 by 2.
No, it's just all 2 by 2.
Oh, then yeah. But when the transpose, all the values have to be the same.
No, like whatever you have for A is transposed as the same element, but in different, if A has a row-wise element, then you have the same elements column-wise. This is what transpose means. So if you have 1, 2 row-wise and 3, 4 row-wise in A, its transpose would be A2 column-wise, 3, 4 column-wise. Let's prove it, whether it's true or not. Triangular, A1, 2. Okay. Symmetric matrix. So let's say we have a symmetric matrix AB, BC. It's a symmetric, right? Because if you look at A transpose, then AB will be AB here, and BC will be BC here. So we have the same thing, AB, BC. So let's take A is AB, BC, row-wise, and let's take another matrix, B, EF, FG. Then it's also a transpose, I mean not transpose, B is equal to B transpose, right? Now let's add them. Oh, before that, we have to prove the 0 matrix. 0. Oh, sorry, it's not vector, it's a matrix, sorry. 0, 2 by 2. We have 0, 0, 0, 0. Is 0 matrix a symmetric matrix? Of course. So it satisfies the first condition. The second condition says add 2 symmetric matrix and see, do you still have a symmetric matrix? So let's add them. We have A plus E. So the first position is A and E. The second position is B and F. So we have B plus F. The third position is B and F, same. So we have B plus F. And the last position is C and G. So we have C plus G. So this is A plus B matrix. Now let's see its transpose. A plus B transpose. So row-wise, we have A plus E, B plus F. So let's write them down column-wise. A plus E, B plus F. Then row-wise, we have B plus F, C plus G. So write them down column-wise. B plus F, C plus G. So if you compare A plus B with A plus B transpose, are the same? Yes, they are. So the sum of 2 symmetric matrix is a symmetric matrix. Second condition fulfilled. And the third one is easy to see, right? You just take A, multiply by a constant, you get the same thing back. So C, not C, I shouldn't say C, K. K times A is AK, BK, BK, CK, which is also a symmetric matrix. Huh? That condition also fulfilled. That means among all 4 questions we have for examples, there are only 2 that actually are subspace of 2 by 2 matrix. One is symmetric and the other one is diagonal. Maisha.
I'm confused about the symmetric one. Can you give an example where it won't work?
Symmetric matrix is a subspace. So it will work for any symmetric matrix.
So a symmetric matrix is a square matrix,
Yes.
always.
Thank you. Brandon, no fun. That's why I'm blessing you. No fun, because you need to remember this. You need to understand this. Question. Okay, so we are done with metric space. Now let's go to polynomial space. So polynomial space is set of all polynomials. Here we have polynomial of 4th degree. So it says determine whether the following are subspace of P4. So set of, the first one is set of all polynomials in P4 of even degree. So P4, it means we have the highest degree 4, okay? And it says, the first question, it says, if you take all the polynomials of 4th degree with even degree, you still get the even degree polynomial. And you have to fulfill all 3 conditions. 0 condition, sum of 2 polynomials condition, multiplied by a constant condition. If you fulfill all 3 conditions, after fulfilling all 3 conditions, do you still have the even degree is a degree 4 polynomial? Think about it. The next one says all the polynomials with degree 3. So you take 2 degree 3 polynomials, you add them, is it a still degree 3 polynomial? If you multiply by a constant, is it still a degree 3 polynomial? And if you multiply by, if you have a 0 polynomial, is it still a degree 3 polynomial? And the last example says all the polynomials such that P of 0 is 0, means it goes to the origin 0, 0. So let's start with the first one. If you take even degree polynomial and is zero polynomial as an even degree polynomial? Maisha?
Yes.
Yes, because 0 to the 4 is even degree polynomial. The answer is 0. Now, if you add 2 degree 4 polynomial, if you add 2 even degree, do you still get an even degree polynomial? Are you sure?
Because x to the 4th plus x to the 4th is just 2x to the 4th.
True, but is it the only thing you have? How about positive x to the 4? If you have, which one are the first one? If you have positive x to the 4 plus x squared, x cubed, and you have negative x to the 4 plus x, and if you add them, what do you get? So this is polynomial 1, P1, and this is second polynomial, P2. You take 2 polynomials, one is x to the 4 plus x cubed, and second polynomial is negative x to the 4 plus x. If you add them, what's the result? X cubed plus x. Is it an even degree polynomial? So, is it a subspace? No, because we found a counterexample. You take any two polynomial with degree 4 and you add them. If you still get a degree 4, if you still get an even polynomial, means your highest degree is either 2 degree or 4 degree, then it's a degree 4 polynomial. But we've not degree 4 polynomial, so it's an even polynomial, even degree. But we found a counterexample. One is positive even degree, one is negative even degree. They cancel out, we get odd degree. So it's not an even degree polynomial. So the first one is no. The second one is degree 3 polynomial.
No, because for the third condition, if you multiply the scalar is itself, it would raise the degree.
No, scalar doesn't have a degree.
If the scalar is x, right?
Scalar is a number.
It's a number. Oh, it has to be a number. Okay.
Degree 3 polynomial is a subspace. Alexander.
Same as the first one.
Same as the first one. You can take any two degree 3 polynomial, add them, maybe they cancel out. For example, one of the polynomial could be x cubed, and other polynomial could be negative x cubed. So if you add P1 and P2, P1 plus P2, do you get a cubic polynomial? No. Or if you want to get convinced, then x cubed. We have space here. We have answer here actually. For example here, cubic degree is 10x cubed, 5x squared, and then another cubic is negative 10x cubed. If you add them, the result is x squared. Not a cubic polynomial anymore. So even degree is not a subspace, odd degree is not a subspace, and the last one says all the polynomials such that P of 0 is 0. Means the polynomial goes through the origin, 0, 0. So if you have a polynomial that satisfies this condition, that when x is 0, your y is 0, is it a subspace for your polynomial space before? Any idea? It means you're looking for, if you're finding a counterexample, you are trying to find a counterexample, two polynomial when you have x0, y0, and when you add them, you still when x is 0, your y is 0. Maisha?
This doesn't work.
Doesn't work? So is it a subspace or not subspace?
Oh.
Not subspace. That means you have to give a counterexample. X squared minus x cubed is one polynomial, and it's P1 of x. So we have when P0, x0, y0 true. And then another one, you have to give a counterexample. So you're adding the same thing twice? You're trying to cheat. No, you cannot add the same thing. You have to get two different vectors or two different polynomials. So if you cannot think of a counterexample, you have to prove it. So let's see. Actually, it is a subspace. So 0, P of 0 is 0. That means 0 is inside our polynomial. Then the scalar multiplication. When you multiply P of 0 by any constant C, we get C times P of 0, but P of 0 is 0. So you get C times 0, which is 0. The constant times the polynomial gives you 0, and they're saying when x is 0, y is 0. So it doesn't matter what x value you have, your y value is always 0. When x is 0, your y is always 0. And when you multiply two same characteristic polynomial, that means P of 0 is 0 and P of 0 is 0. So for both P and Q polynomial, when x is 0, y is 0. So when you add them, we get P of 0 plus Q of 0. But P of 0 is 0, Q of 0 is also 0. So the result is 0. So when you add two polynomials with the same characteristic, the result is 0. When you multiply them by a constant, the result is still 0. And 0 polynomial is it's still 0. So they satisfy all three conditions. So this is the only example that is a subspace of P4.
Sorry, what does P4 mean?
All the polynomial is degree 4.
Oh,
It's a space of all the polynomial with the highest degree 4. So it could have lower degree, but the highest cannot be more than 4. Any question? So remember, in the exam, I'm going to ask one of these, either from R2, R3, or the metric space or the polynomial space. One question from any of these 4 spaces. Prove that one example or a set is a subspace or not. Actually, I'm going to give 2. One will be a subspace, one will be not a subspace. So for not a subspace, don't prove anything. Just find a counterexample.
When is the next exam?
20 what?
24.
24. Yeah. I'll try to make it shorter, which is doable in 1 hour, 15 minutes. So even though you're learning many materials, but I'm going to give you a review sheet. So you're going to know exactly what you have to study. But to do those questions, you need background information. So I'm providing you all with all the background information so that you can actually do some questions. So you're done with subspace. Now you're going to do something little bit fun, not fun actually. Little bit you already know, but you don't know that it's you already whatever you know. Null space. So we learned about subspace, and now we are learning about null space. Null. The null space is related to it 0. So the null space, or it has another name, kernel. The null space of the kernel of a matrix is the set of all solutions to the homogeneous equation Ax equals 0. In other words, if you solve a matrix if you solve a matrix that has your B matrix is 0, and then whatever solution you get, that solution is the null space. And combining with all those null vector, the null space, we represent the null space by null of A or kernel of A. And if you have a bunch of a bunch of vectors in a space, then we call it the nullity of A. Means what's the dimension for your null space? The dimension for the null space is how many vectors you have in your solution. And what's the solution? When you solve for a variable, how many solutions you have, or how many columns you have as a solution. That's the null space. Example. Let's say we have a matrix 2, 1, 1, 2. And we want to find out what's the null space of this matrix, or what's the dimension of this null space for this matrix. So what you're going to do is you're going to apply reduced echelon form. When you apply reduced echelon form, so first we rewrite Ax equals B, or B here is 0 matrix, okay? So you don't have to write B, but if you want, you can write B as an augmented matrix. So you can work with only the coefficient matrix or with the augmented matrix, it's up to you. But your goal is to do reduced echelon form. When you apply reduced echelon form, the 2, 1, 1, 2 becomes 1, 1/2 row-wise, 0, 1 row-wise. And then you're going to solve. So here they're saying that our x1, the first column is x1, the second column is x2. So the first line is telling us x1 plus x2, 1/2 x2 is 0. That means x1 is negative 1/2 x2. The second line is telling us our x2 is 0. If x2 is 0 and x1 is f of x2, that means x1 is also 0. So it's a back substitution. So x1 is 0, x2 is 0. That means the only solution you have is a 0 vector, 0, 0. So that's the null of A, 0, 0. And the dimension, which is the nullity of A, is 1 because we have only one vector in a solution set. So nullity of A is 1 because we have only one vector.
Oh, could you just read the second line? You have x1 plus 1/2 x2
This
equals
one.
0. No, what you wrote.
This one and this one, I see. So here I goes on the same row, so you can see the information. X1 plus 1/2 x row is 0. So when you solve for x1, it's x1 is negative 1/2 x2.
Oh, that's x2, okay.
Sorry. It's two, Brendan.
Why would you not just keep going, like to make it, like fully reduced?
If you want, you can do that, but if you don't want, you don't have to do that. Your goal is to get the solution. Okay. So for this type of question, raw echelon form is better than using what do you call inverse matrix. Okay, the next example. We have a 4x2 matrix. Row wise, it's 1, 2, -3, -1. The second row is -2, -4, 6, 3. So my question is this an augmented matrix or a coefficient matrix? Maisha? Nope. For augmented matrix, remember, for B is 0, 0. Do you see 0, 0 in this matrix given to you as the last column? No. That means it's not augmented, it's coefficient. So if it's coefficient, so how many variables you have then? 4. x1, x2, x3, x4. So if you want to write as an augmented matrix, you have to write 0, 0, a bar between the third column and the fourth column. So the fourth column and the 0, 0 column. So this is your B. And now you cannot find its inverse because why? Why the inverse doesn't exist for this matrix?
It's not a square.
It's not a square. So trying to find inverse is useless. So we have to use raw echelon form or reduced raw echelon form. So let's find it. So our first goal is to get rid of the -2 from the second column. Sorry, first row, first column, second row. So we are changing row 2. Let me erase this. So what is our new row 2? The old row 2 plus what?
Well,
2 row 1. So if you multiply the row 1 by 2, we get 2, 4, -6, -2, 0. And when you add these two, we get a new matrix. 1, 2, -3, -1, 0. And then 2 minus 2 is 0. 4 minus 4 is 0. -6 minus 6 is 0. -2 minus -2 plus 3 is 1. infinite solution. Good. That means we are going to have more than one, most likely we are going to have more than one vector in our null space. Maisha.
Instead of doing like the inverse or row echelon, can't you just turn it into the regular equations?
But you're going to solve the equation.
So, like, can you just use x1, x2, x3, x4 equals, oh, it's a coefficient matrix.
So you have to solve for x1, x2, x3, x4.
So why do we have the bar?
We don't have the bar. So if you want to place the bar to make it look, make it as an augmented matrix, you can do that. If you don't want to, you don't have to do that. It doesn't matter what you do, the right side will always be 0, right? The B part is always 0. That's why you don't have augmented matrix, your coefficient matrix.
Okay. How do you know the B part is always 0?
Because the null space is only when the B is 0. We can find the null space for homogeneous system of equation. Not all the matrix, only for homogeneous system of equation. Homogeneous means your B, the constant matrix is 0.
How do you know?
Because we, among all those system of equations, you're taking only those system of equations that have the right side is 0.
But I thought all square matrices are coefficient matrices and everything else is augmented.
No, that's not true. You make augmented matrix or you make the coefficient matrix. So here, what type of matrix you're working with is only those matrix, we call them homogeneous, but what is homogeneous? All those matrix, they have a equals to 0. It means the B matrix is 0 matrix. Not in the coefficient. So we have AX equals B, right? What is your B matrix? Right. So you can only work with A. You don't need the B. You reduce your A and C. What do you have?
But I don't want.
It doesn't even have a. It's singular because inverse doesn't exist. But we cannot say singular because when the determinant is 0, that's a singular. This one doesn't even have a determinant. It's not a square matrix. So it's not a singular matrix. It's just non-square matrix. It's a normal matrix full with system of equations from homogeneous system. B is 0. All the system of equations that has your B, the right side of the equal sign is 0.
All the square matrices were coefficient and all the non-square matrices were augmented matrices.
No, you know it wrong. So currently we have 1, 2, -3, -1 on the first row. We can change -1, right? We can make -1 to 0. So how do you make it? Row 2. So we have 1, 2, -3, 0. And then we have 0, 0, 0, 1, and then 0, 0.
We put on 1 minus or 2 with the
No, add plus R1 plus R2. So we are done. Now we just rewrite our information. What is the second row telling us? So this is X1, X2, X3, and X4. So what's the second row is telling us? X4 is 0. And what's the first row is telling us? So X1 plus 2X2 minus 3X3 equals 0. Right? Now we can at least solve for X1. So X1 is -2X2 positive 3X3. And our X4 is 0. So this is the solution for infinite solution. Now you have to write them as vectors. So what you do, that's the important thing. The x1 is 0x1, negative 2x2, positive 3x3, and 0x4. Right? x1 is 0x1, negative 2x2, positive 3x3, and then 0x4. Right? Do you see what I did? Even though we don't have 0, we don't have x1 or x4, but I placed them as 0 coefficients. Now x2, what is x2? No,
Oh,
x2 is independent, right?
yeah.
x2 is x2, and what is x3? What is x3? x3 is x3. Because they don't have any equation for them. x2 and x3, they're independent. x1 depends on them. And x4 has a single solution, 0. Now we are going to write all of these as a matrix format. Our x2 is 0x1 plus x2 is x2 itself, 0x3 and 0x4. What does that mean? It means x2 is x2. The same information I have here. Now x3 is same thing. It's 0x1, 0x2, but x3 itself and 0x4. So x3 is x3. This is what I written here. x3 is x3. Everything else is 0. Lastly, we have x4. x4 is 0 for everything, right? 0x1, 0x2, 0x3, 0x4. So it's 0, 0, 0, 0. Because the solution for x4 is 0. Okay? Now, how do you find the null space? The null space of A contains of all the non-zero vectors. So here we have this vector and this vector that doesn't have all elements 0. We disregard the first one and the fourth one because all the elements are 0 here, all the coefficients. So disregard the first column and the last column and write down these two columns with only coefficients. So we have negative 2, 1, 0, 0. That's our one vector. And we have 3, 0, 1, 0. That's our another vector. So a null space, we use curly parentheses, and also we use another word. So null space of A is a span of these two vectors. It means our null space is consists of all the linear combinations of these two vectors only. That means you know what's the nullity, means the dimension. What's the nullity of A? What's the dimension for this space? Means how many vectors you have in this space? How many vectors? 2. So nullity is 2. So again, null space is the solution for homogeneous system of equations. But we don't write the solution as equations. We write the solution as a vector. How do you write it? Write a matrix with all the information and then figure out which two columns or which columns have non-zero entries. If you have anything non-zero entries, then you write them down as a vector, as a column vector with only the coefficients. And then depending on how many column vectors you have, that's the dimension of your space. So previously we had only one vector, which was 0 vector. So our nullity was 1. This system of equations, they have 2 vectors in the null space. So our nullity is 2.
Could you repeat what you said, the definition of a null space is?
The null space is set of all solutions to the homogeneous equations AX equals 0.
Does the null space exist in vector space or they're just?
Null
separate?
space is a vector space.
Oh, it is.
Mhm. It is a subspace. In the book, if you read book, in the book they actually prove null space is a subspace. But I'm not going to prove anything. So this will be in the exam. My pen, where is my pen? So exam question. I'm going to give you one smaller matrix to work with, and you're going to find the null space, means the vectors, and then tell us about the nullity, means how many vectors you have. Is there anybody who is lost? Oh, I didn't take the attendance. Let me take the attendance. Any question? Oh, and we can write in another method. So we know that our solution has only x2 and x3 independent. So you can write x2 times the first column vector -2, 1, 0, 0. And then our second independent vector is x3. So plus x3 times the second column vector 3, 0, 1, 0. But the formal way of writing the null space is null of A equals the span with the curly bracket, and then you put all the vectors you found from the solution set. And if you want, you can try this example. But can I change my page, Caroline?
No.
No? Okay.
Yeah.
Okay, so we have around 7 minutes. Try this one, find the null space. And this is actually easy one. Let me take the attendance. Brendan C. Here. So what days today? November 3. Joseph. Justin. Gibran. Shibu. Absent. Michelle. Absent. Jack. Ashif. Darius. Winston. Abigail. Shane. Emily. Anar. Absent. Christine. Edison. Maisha here. Brandon here. Alvin here. Shafal. Absent. Alexander here. Shitila here. Wenchuan. And Kylon here. So let's see who's at someone still here. Justin. Science. Chef. Let's see. So I didn't count all these days. So whatever days I counted, let me see, I had 3 absence so far. So I counted how many days? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I counted only 10 days. And how many lectures today? 15? 16. So you count 6 days. So in our next class, which is Wednesday, we are going to do, we are going to talk about linear combination, spanning, bases, all these things. And you are going to have fun watching some videos in our next class. Question. Alvin, are you done already? Great. Can you tell me the answer? What do you have? Mm-hmm. Mm-hmm. That's it. So what's the nullity? Means the dimension 2. Is anybody else is done? No? Okay, we have 5 minutes. Let's try it. So our goal is to get 2 become 0 and make -1 to 0. So we're going to change row 2 and row 3. So what did you do, Alvin? How did you change row 2? To row 1 and row 3? Row 3, row 1. So what's the new matrix you have? 1, 3, -4, and then 0, -7, +7, 0, 0, 0. Then you are going to change row 2. Or you didn't do divided by -7 to make it simpler. So we have 1, 3, -4, 0, 1, -1, 0, 0, 0. You can stop here, or if you want, you can get rid of this. Or let's keep this actually. Let's get rid of this. Make it 0. So our row 1 will be new row 1, the row 1 minus 3 row 2. So row 1 is 1, 3, -4. 3 row 2 is 0, 3, -3. And when you subtract, the sign will change. So you get 1, 0, -1. So 1, 0, -1, 0, 1, -1, and 0, 0, 0. So the first line is telling us x1 minus x3 is 0. The second line is telling us x2 minus x3 is 0. The first line is telling us x1 is x3. The second line is telling us x2 is also x3. So if you write down this information in a matrix form, we have x1 is 0x1, 0x2, and then 1x3. So x1 is x3. The next line is telling us x2 is 0x1, 0x2, and x3. It means x2 is x3. So we have x3. It's 0x1, 0x2. X3 is x3, x3, x3. So x3 is independent. x3 is x3, x2 is x3, x1 is x3. They all are x3. So why do we have issues? So we have our null of A is the span of 1, 1, 1. This 1, 1, 1 is coming from these coefficients. 1x1, 1x1, 1x. So 1x3, 1x3, 1x3. So what's the nullity? It's dimension of a null space. 1. Do we have the answer? Yeah, the answer. 1, 1, 1. So main idea, do the reduced echelon form or at least echelon form. Even if you do back substitution, you have to go all the way back substitution. And then you write the solution down in matrix format so you can see how many columns you have with non-zero entries. Based on how many columns you have non-zero entries, you put those in your parentheses, curly brackets, and depending on how many vectors we have, that's your nullity, this dimension. Okay? So, have a good night. See you all on Wednesday with more information. So be safe, everyone.